In this section, we're going to think about how we can take derivatives of multivariate functions and what does it mean. So before we jump right in, let's quickly review single variable derivatives. And then we could elaborate on that idea to define what it means for a multivariable derivative. Okay, so let's look at an example. F of x equals 1/8 x squared. Okay, so I could take the derivative, just a little power rule here, bring down the 2, subtract 1 to get my new power, so it's 2/8 x to the 1. If I simplify, I get 1/4 x. Okay, so great, I found my derivative. Now, what does it tell us? The derivative tells us the slope of the tangent line to the curve at any value of x that we pick, right? Another way to phrase it is it gives us the instantaneous rate of change of the curve. All right, so for example, if I wanted to know the instantaneous rate of change at 4, it's 1, right? The slope of the tangent line at x equals 4 is 1. So let's take a look at what this means. This is our function, f of x equals 1/8 x squared. Here's the point that we want to be tangent to, where the x is 4, right? And so using the derivative, we found that the slope of the tangent line is equal to 1. And so using a slope of 1, I'll write the 1 there just to make it clear. And then with a little transformations to make sure the line goes through the tangent point, we can see the tangent line. Okay? Now, what would it mean in a multivariable setting? How do we even think about a derivative in a multivariable setting? Okay, so let's take as our example the function f of xy equals 1/8 y squared minus xy minus x squared. All right? And it's going to be helpful if we think about the tangent behavior at a particular point. Just like here, we looked at how the slope of the tangent line is at x equals 4. All right, so here let's consider specifically the xy point 1, 2. Okay. So here's the surface we're dealing with. Okay. Interesting looking surface. And we're interested in the tangent behavior at this point. Now, what I want to emphasize is that if we look at this in different directions, the tangent behavior will be different. Okay? Because there are lots of ways we can go through that point, right? There are lots of different paths through that point. And depending on the path, our tangent behavior will be different, right? If we look at this path, let me get this out of the way. If we look at this path, if we kind of restrict ourselves to 2 dimensions, it looks like we are increasing, right? The slope of the tangent line at the point from going left to right would be going uphill. But if we look along a different path, say this one right here, get rid of that. Look at the curve now going left to right. Now it looks like we're going downhill, doesn't it? We're decreasing. The slope would be negative. So looking in different directions, the slope of the tangent line would be different. And so how do we describe the tangent behavior for a surface when there's so many different directions and different ways to look at it? Okay? So what we're going to do is we are going to focus on just 2 directions. And as we'll eventually learn, those two directions will tell us an awful lot about the behavior, the tangent behavior of this surface in all directions. All right. So what I want to do is I want to look at the behavior of the tangent behavior to the surface going just in the x direction. So just in the trace where the the y direction. Just in the trace with the x value fixed and the y value changes. Okay. And then we'll also look at the behavior of the surface with the y value fixed going in the x direction. Now, each of these on their own, notice, each of these would just be a two-dimensional curve, right? We're kind of stripping out the third dimension. We're thinking of it as a two-dimensional curve. And so we can use single variable calculus to find the tangent line to a point on this curve, just like we do for this example, okay? Or if I look at the other curve, again, I'm stripping out one of the variables, thinking about this as a curve in just two dimensions. I can find the derivative if I just look at this trace with the y value fixed as the x value changes, okay? So let's think about how we want to do this. The idea here is that we will fix one of the variables. We will make sure it doesn't move because we're going to look at a trace. So we're going to look at the cross section or the trace where x is equal to 1, right? So we want to look at this surface. We're going to let the y change, but we're going to fix the x at 1. So the x is going to be a constant value. We're only looking at how the surface changes as we change the y value, as we change the y variable, keeping the x variable fixed. Okay? So what I want to do is I want to take the derivative with respect to y. Notice I'm not going to use prime here. Because I've got multiple variables going on, I don't want to use prime. Prime's not very clear. It's fine if there's only one variable. It's clear that, oh, if I'm taking a derivative, it must be with respect to x. But with multiple variables, even though I'm plugging in one for x, we don't want to muddy the waters with just saying prime and then leave the person looking at your work to guess, is that a derivative with respect to the x variable or with respect to the y variable? I've also forgotten to plug in the fixed values of x here, so let me do that. So we're plugging in 1 for x there and there. So we get 1/8 y squared minus y minus 1. Okay, so if I take the derivative of that, derivative of this, okay, 1/8 is just a constant, comes along for the ride, and I just need a few power rules here. Derivative of y squared is 2y. Derivative of negative y is -1. And derivative of -1, that's a constant all by itself, so it's 0. Okay, so that is my derivative with x fixed looking only in the y direction, looking at only the direction where the y changes, only the trace where the y changes, and x is held fixed at 1. If I want to know the slope of the tangent line to this particular trace of the surface, then all I need to do is plug in the other value, the y value, and it will give me the slope of the tangent line to that trace. Okay, so the x stays fixed at 1, but I'm going to plug in 2 for y. And this, you can really see why we don't want to use the prime here, because once I start plugging things in, it's not clear which one I'm treating as a fixed value and which one I treated as the variable when I took the derivative, right? And that's why we use this notation. We need to be clear which variable are we differentiating with respect to. Okay, so if I just plug in the 2, get 2 times 2, that's 4, minus 1 is 3, I get 3/8. Okay, So that is the slope of the tangent line to this trace at that point. Let's see what that looks like on the graph. Okay, so this is the trace we're looking at, the trace where I'm letting y change, but I'm fixing x at 1. Okay, and using the derivative, I was able to find the slope of the tangent line, and using that, I could construct the line tangent to the surface in that direction. Let me hide the surface, it'll be a little bit easier to see. Okay, so we're just finding a single variable tangent line, just like we did here. Okay, by fixing the x value, we're looking at a trace, and that reduces the problem to one variable. Okay, now of course that one variable doesn't contain all the information we need, right? It doesn't have everything we need to know about the tangent behavior to that surface. There's a whole other direction we can look in, right? In fact, there's many other directions, but there's one other direction that we will look in. Okay, so we saw the behavior, the tangent behavior of the surface with x fixed and allowing y to change. Now we want to look in the other direction. Now we're going to fix the y value and allow x to change. We're going to look at a different trace. Okay, so now I'm going to set y equal to 2. So my function becomes fx comma 2, fixing the y value but letting the x value change. So I'm going to look at how the function value changes, the rate of changes of the function, as I let x change, but I hold y fixed. Okay, so the function is 1/8 y squared minus x times y equals 2 minus x squared. So I plugged in the 2's for the y's, and that simplifies to 1/8 4 minus 2x minus x squared. So if I take the derivative of this now, this trace, with respect to x, I get, so the 1/8 in front is a constant, comes along for the ride. And then inside the parentheses, I have a constant all by itself. Derivative of a constant is 0. Derivative of negative 2x is negative 2. And the derivative of negative x squared with respect to x is negative 2x. Okay? If I factor out the negative 2, cancel with the 8, I end up getting negative 1/4 1 plus x. Okay? Notice I factored out the negative also. I factored out the 2, I factored out the negative. The negative's out here. 2 divided by 8 is 1/4, leaving me 1 plus x inside. Okay? So anywhere along that trace, all I need to do now is plug in the x value, and I can find the tangent behavior in that direction. Specifically, if I'm interested in the tangent behavior at the particular point 1, 2, I can plug in a 2 for the y. I'm sorry, other way around. 1 for the x, right? I've already set y equal to 2. I've fixed it at 2. That's the trace I'm looking at. So I'm interested in the particular point along that trace where x is equal to 1. So plug in 1 for x. 1 plus 1 is 2. Divided by 4, I'm going to get negative 1/2 as the slope of the tangent line along that trace, as letting the x change and holding the y fixed at 1. All right, so let's see what that looks like. Okay, so let me hide my other trace. So this is the trace we're looking at. Okay, the y value's fixed. The curve changes as we move in the x direction, right? And we're interested in the tangent behavior specifically along this trace at the point 1, 2. So let's look at, there we go. That's the tangent line. It has a slope of 1/2. You got to be careful looking at directions though. Does this, wait a second, slope of negative 1/2. Okay, Does this look like it has a slope of -1/2? Well, no, it's going uphill, right? It should have a positive slope. But the -1/2 means as we increase x by 2 units, as we go 2 units in the positive x direction, the function value or z value should go down by 1. Okay? But here, if we go to the right, we're actually going in the negative x direction. Do you see that? The positive x direction, you got to be real careful with your orientation here, is actually over here. So if I flip it all the way around, now it matches what our intuition says. Left to right, now we're going downhill because now going right is the positive x direction. Okay? And so we could see if we go 2 units right, it looks like we might go about 1 unit down on that line. Okay? And so by capturing all this information, we can learn about the tangent behavior of the surface at any given point by just looking at the single variable derivative along a trace. Okay? These derivatives are called partial derivatives. Because unlike with the single variable function, it's not telling me everything we need to know about the tangent behavior at a point, right? It's telling me part of the information. It's a partial derivative. It's only telling me the tangent behavior along a trace of the surface in the x direction or in the y direction. So we found the partial derivative along the trace x equals 1, letting the y change and fixing the x at 1, right? We did the same thing for y equals 2. But what if we are interested in the tangent behavior at another point, right? The nice thing about the derivative here is it tells us the slope of the tangent line for any value of x we want to do. We only have to take the derivative once, right? And then once we take that derivative, any point we want to find the tangent behavior to, we just plug in the corresponding value of x and we can find it like that. Okay? We don't have to take the derivative every single time. But here we kind of do, don't we? Unless I happen to be looking along this same trace or along that same trace, I would need to take the derivative all over again. For example, let's look at a whole different point. Okay, and we'll be fast about this. Let's say we look at the point -3, 2. Okay, and let's just look along the trace where we hold x fixed at -3. All right, so f of -3y becomes 1/8 y squared minus xy, so minus -3y, plus x squared, so plus -3 squared. So that's y squared plus 3y plus 9. So if I take the derivative with respect to y, seeing how the function changes along that trace, I get 1/8 times 2y plus 3. Okay? Do we really want to have to do all of that work every single time we want to take a derivative? Every single time we want to find tangent behavior? It turns out we don't need to. Okay? Because there is a pattern here. Take a look at this function and take a look at this function. These are the two functions where we hold y fixed. All right? Now look at what happens when we take the derivative. We get 2 times y minus 1. 2 times y is there. The minus 1 is right here. Notice the minus 1 was just the value of x, right? Minus x. We have the same thing here. Derivative of the y squared is the same. Derivative of the x times the y is also the same. The y goes away, but we're treating the x value as a constant, -3. So I have minus that x value, minus -3. Okay? And the x squared at the end, which in this case is minus x squared, so that's minus 1. I'm treating the x as a constant, so the derivative just goes to 0. It disappears from the derivative of this trace, right? Same thing here. I have a 9 at the end from the negative 3 squared. Okay. And you know what? I think I got the sign wrong. This should be minus. Not that it really matters for this example. Okay. But the derivative of negative 9 is also 0. So what we notice is that there's a pattern here. Rather than having to plug in the x that we're holding fixed before we take the derivative, what if we just mentally make a note that the x is fixed and I'm only looking at the direction of y? And then after I take the derivative, I could plug in whatever x and y I want, understanding that the trace, that the derivative corresponds to the trace where x is fixed. Okay, let me show you what I mean. So let me just rewrite the function for reference. 1/8 y squared minus xy plus x squared. Okay, so now I'm going to hold x fixed. Okay, but I'm not saying what constant x is equal to. I'm not saying which trace we're looking at. I'm just saying we are treating x as a constant. Okay, now I can take that f of xy, that function, and I can take that partial derivative in the y direction. All right. So partial derivative in the y direction, that means I'm going to treat x as a constant. I'm only thinking about how this function changes as y changes. Okay, so 1/8 stays 1/8. Derivative of y squared, I'm treating y as a variable, so I take the derivative of this normally. Derivative of y squared with respect to y is 2y. Okay, now go to the next term. What about the derivative of negative xy? Well, I'm going to hold x fixed. So I'm going to treat x as a constant, and I'm only going to look at how this changes with respect to y. Okay, so if x is a constant, then it just comes along for the ride, and I just multiply by the derivative of y. So I get negative x times the derivative of y, which is 1. Right? And just to be clear, this is just like if I took the derivative with respect to y of 3y. Okay, what would you do? The 3 comes along for the ride, the derivative of y is 1. Right? Here I'm treating x as a constant. X comes along for the ride, derivative of y is 1. And finally, derivative of x squared. I'm treating x as fixed. So it's a constant, which means x squared is a constant all by itself. Derivative of x squared is 0. And I got the sign wrong again, didn't I? It should be a minus x squared. Doesn't matter, it's still constant. Derivative of minus x squared is 0, so it goes away. Okay? And so I get 1/8 times 2y minus x. That is the partial derivative of f in the direction of y. For any trace where x is fixed, I can find, this now tells me the partial derivative of the curve as we hold x fixed and as we let y change. Okay, so for example, the very first one we did, we saw that the derivative where we hold x equal to 1 fixed, and we let y change, but we're interested in the behavior of the change when y is 2, we found that that derivative was 3/8. Okay, let's plug that in. So if I plug in 1 for x and 2 for y, I get 1/8, 2 times 2 for y minus 1 for x. I get 3/8. The exact same answer. Okay? So rather than having to plug in the particular fixed value we're interested in beforehand, we can wait until after. And now at any point we're interested in, I can look at the trace with x fixed moving in the y direction through that point, and I can plug in the point and find the slope of the tangent line to that trace, okay, with that x value fixed, right? Similarly, if I want the derivative, the partial derivative in the x direction, holding y fixed, I get the 1/8 in front, just comes along for the ride. Derivative of y squared, well, now I'm holding y fixed. I'm taking the derivative with respect to x. Any variable other than the x, I'm going to treat as a constant. So specifically the y, I'm treating as a constant. Y squared is a constant. Derivative of a constant is 0. Okay, what about negative xy? Okay, the negative is a constant, comes along for the ride. The y is a constant, comes along for the ride. But x, I'm treating as the variable. I'm looking at the change in the x direction, so I'm letting the x vary. I'm holding y fixed, but I'm letting the x vary. So the derivative of x with respect to x is 1. I've got the negative, I've got the y, and then the derivative of x is 1. Okay, and finally, derivative of negative x squared with respect to x is negative 2x. And so I can find these partial derivatives, which will tell me the tangent behavior in these different directions, where we hold x fixed and let y change, or we hold y fixed and we let x change. Okay, and we can do it generally, so that if I want to know the tangent behavior at any point, I could just plug into these partial derivatives and find the tangent behavior of the surface at that point. Okay. Now, you may have noticed that I've slightly changed my notation. Before, I was using ddy and ddx, just like we do in single variable calculus. Okay? But in multivariable calculus, we want to emphasize the fact that I'm taking the derivative with respect to y, but I'm treating all the other variables as fixed. Or I'm taking the derivative with respect to x, but I'm treating all the other variables as fixed. Okay? For these partial derivatives, we use this symbol. It's not quite a d. It's got a curve at the top, right? It's called a partial symbol. And we use that when we want to emphasize that we're taking a partial derivative rather than a full derivative like we do in single variable calculus. All right? So that's one way we can notate a partial derivative. There are other ways that we can notate a partial derivative. So this one you've seen, partial f partial x, that's the partial derivative of f with respect to x. We're taking the derivative with respect to x, the other variables we're treating as a constant. But that's kind of a lot to write, isn't it? So sometimes to simplify things, we use a subscript instead. This means exactly the same thing, the partial derivative of f with respect to variable x. Similarly, partial derivative of f with respect to y, I can write f sub y. And if there is a third variable, then I could take the partial derivative of f with respect to z, and that is f sub z. Different ways to write the same thing. Sometimes it's convenient to combine all of your partial derivatives into a single vector. The notation for that is the gradient. Okay, this upside down triangle symbol. It's called a nabla, but we'll call it the gradient symbol. Okay, the gradient symbol says, give me the vector of all partial derivatives of function f in order. Okay, so function f is a two-variable function. Then we'd have a vector with two components. The first component is the partial derivative of f with respect to x. The second component is the partial derivative of f with respect to y. If f has a third variable, okay, maybe I'll use a different letter. Of course, a function doesn't have to be f, right? We could use a different name. So if a function has a third variable, x, y, z, then now the gradient is the vector of all three partial derivatives. The partial derivative of g with respect to x, the partial derivative of g with respect to y, and the partial derivative of g with respect to z. So I hope you now have some intuition regarding these partial derivatives. But sometimes it will be helpful to also know the exact definition. So let's define how we find the partial derivative of a function. What is technically a partial derivative? So let's let f be a function of two variables and be a differentiable function of two variables, meaning we could take the derivative of it. Just like in single variable calculus, there will be functions where there are points that we can't take the derivative of. But let f of xy be a differentiable function of two variables. Then the partial derivative of f with respect to x is equal to, and we're going to define this almost the same way as we define the derivative in single variable calculus. We're going to take the limit as h goes to 0. But in this case, we're only interested in the behavior of the function as the x variable changes. So I'm going to look at f of x plus h comma y and then subtract f of x comma y. Okay, the y is the same in both expressions, in both terms. But I'm changing the x value, right? Just a little bit. H should be close to 0, right? So I'm looking, hey, if I change the x a little bit, then what happens when I subtract the function values? How do those function values change? Right? And then to offset the fact that I'll be changing x by a very little amount, I divide by h. Okay, that somewhat normalizes the difference that we're looking at. So we say, hey, if we change x, how does the function values change? What's the difference between them? Okay, holding y fixed, only the x is changing here, right? And similarly, let me add a word there to make the sentence make sense. If I look at the partial derivative of f with respect to y, I'm going to look at the difference between the function's values for different values of y, but with the same value of x. Okay, so now the x is held constant. It's the same in both function evaluations, but the y changes. Here I'm looking at y, and here I increase y a little bit. I'm changing y a little bit by just that small value of h. And I want to see if I change y by that small value, then how does the function values change? What's the difference between them? How much has my function changed? Okay? We will occasionally have need to use this definition. Now, of course, this is the definition for two variables. If there is a third variable, you would throw that in, right? I'd have comma z over here, I'd have comma z over here, and I would treat z as a constant if I'm taking the partial derivative of f with respect to x. The z would not change, only the x would change, okay? Let's take a look at some examples. Here we have a function z equals cosine x squared y plus y cubed. We want to find the partial derivative of z with respect to x and the partial derivative of z with respect to y. Okay, so let's start with partial derivative of z with respect to x. So I'm going to treat x as the variable. I'm going to treat y as a constant. Okay, so let's start with cosine x squared y. Now, this isn't just cosine of the variable, which means I'm going to need a chain rule, right? because the thing inside isn't just x. So using a chain rule, I can ignore the nastiness in here and just focus on the derivative of this. So derivative of cosine of something is negative sine of the something. Notice I'm leaving the something the same. Chain rule says I could do that. I could ignore this in the first step as long as when I'm done, I multiply by its derivative. So the derivative of x squared y, well, derivative of x squared is 2x, and then y I'm treating as a constant, so it just comes along for the ride. Okay? And then plus the derivative of y cubed, I'm treating it as a constant. I'm differentiating with respect to x, so derivative of y cubed, just 0, goes away. Okay? So this is my final answer, and I could just tidy it up a little bit just by moving the 2xy to the front. Okay. Now let's take the partial derivative of z with respect to variable y. Okay. So similar issue here, but now we're treating y as the variable and x as the constant. So as we take the derivative of this, again, it's not just the variable in here. It's not just y. So when we take the derivative, we need a chain rule. Derivative cosine of something is negative sine of the something, times, according to the chain rule, times the derivative of the something. Derivative of x squared y with respect to y is just x squared. X squared is a constant, so it comes along for the ride. Derivative of y is just 1, so I'll just have the x squared there. Okay, plus the derivative of y cubed with respect to variable y. That's just a standard power rule, 3y squared. If I'm writing this, I'd just rearrange things a little bit. I'd put the 3y squared first. Mathematicians, we usually don't like to have terms with a negative at the very front of our expression if we can help it. Sometimes it's unavoidable, but we like to leave it out if we can. It means you're less likely to drop the negative. And so I'll put minus x squared sine of x squared y at the end there. And so there's my partial derivative of z with respect to y. All right. Example 2. Z is equal to the square root of x squared plus y squared. We want to find the partial derivative of z with respect to x, the partial derivative of z with respect to y. Okay, so partial derivative of z with respect to x, we're going to treat x as the variable, y as a constant. All right, now before I jump into it, we usually don't like to write square roots when we're taking our derivative. We usually like to convert that to a power before we differentiate. So let me just rewrite this as x squared plus y squared to the 1/2 power. Okay, so with that in mind, the very first thing I need to do is the outermost function, which is the 1/2 power. The inside isn't just x, our variable we're differentiating with respect to. So I'm going to need a chain rule also. All right, so apply the power rule to that outermost power. 1/2 minus 1 is negative 1/2. It's my new power. Then multiply by the derivative of the inside. Derivative of the inside is the x squared plus y squared. Derivative of x squared with respect to x is 2x. Derivative of y squared with respect to x is 0 because we're treating it as a constant. Okay, so that's my answer. I could tidy it up a little bit. I could cancel the 2's. And then negative 1/2 power, that means that will go in the denominator. The negative means it goes in the denominator. The half means square root. So I get square root of x squared plus y squared in the denominator, and all that's left in the numerator is the 1 times the x. So that's a fully simplified partial derivative of z with respect to x. Now, if you're real on top of things, your partial derivative of z with respect to y, you will notice that there's a symmetry here. X and y, there's no difference between them. If I swap x and y, I'd have exactly the same function, right? Which means the derivative would be exactly the same. I would just swap x and y. Okay, I'm going to end up with y over square root of x squared plus y squared. Okay, now if that's a little too fast for you, let's go ahead and do it the long way. We do it exactly the same. I've got half power, so do the power rule. I get 1/2 of the inside, x squared plus y squared, and then 1 minus the old power, or the old power minus 1 gives me my new power of negative 1/2. Multiplied by the derivative of the inside, since I'm taking the derivative with respect to y, I'm treating x as a constant, y as the variable. The derivative is 2y. Cancel the 2's just as before. Negative half power means this term will go in the denominator because of the negative, and the half means I'll get a square root. And in the numerator, I just have the 1 left up there and the y. 1 times y is just y. Okay? Okay, so that's example 2. Now on to example 3. Given f of xy is equal to xy divided by x squared plus y, we want to find the partial derivatives of f with respect to variables x and y. Okay? So partial derivative of f with respect to x. Now, we could write the x comma y here if we want to. I'm going to leave it off. Okay, just know implicitly that it is there. A lot of times mathematicians will do that. They will leave off the of x comma y or of whatever on a function just because we start using so many symbols. It just makes things a little too busy. It distracts us from what's really mattering. Okay, so know that if I'm leaving it off, I'm still dealing with a function of x and y. Okay, but I'm leaving it off as a choice just to make the expression a little less busy, a little less distracting, help us to focus on the important stuff. Okay? So I'm taking the partial derivative of f with respect to x. That means x is the variable, y is a constant. Right? I've got a quotient here, so I'm going to need the quotient rule. So the derivative of the numerator with respect to x, derivative of x is 1. The y just comes along for the ride because it's a constant. Times the denominator unchanged. Minus, now swap the roles. Now you leave the numerator unchanged and take the derivative of the denominator. The derivative of the denominator with respect to variable x is just 2x. Derivative of the x squared is 2x. And the derivative of y, since it's a constant, derivative of a constant all by itself is 0. And that's all over my denominator squared. Okay? And so if we just wanted to tidy up, we could distribute this, we could multiply that together, we get x squared y plus y squared minus 2x squared y all over x squared plus y squared. And then I have some common terms that I can combine. So I get y squared minus 2x squared y. I'm sorry, just minus x squared y. Once I combine those terms, one of these minus 2 of these gives me minus 1 of them. Divided by x squared plus y squared. Okay? Fully simplified partial derivative of f with respect to variable x. Now let's do it with respect to variable y. We're going to need the quotient rule again. Okay? But now we're differentiating with respect to y, treating y as a variable, treating x as a constant. Okay? So the derivative of a constant times variable y is just the constant. Just x. Times the denominator unchanged. Minus, and now swap roles. Now it's the numerator unchanged times the derivative of the denominator. Derivative of x squared with respect to variable y is just 0. We're treating x as a constant. Derivative of y with respect to variable y is 1. So I just get 1 as the derivative of my denominator. And then to finish off my quotient rule, all of that is over my denominator squared. Okay, let's distribute, combine like terms, tidy up. I get x cubed plus xy from the distribution, and then here I get minus xy. And so we could see the xy and the negative xy on top here will cancel, leaving me just x cubed in the numerator. Okay, and we have our partial derivatives of f with respect to x and with respect to y. All right, one more example. This is a 3-variable function, and we want to find the gradient of that 3-variable function. Now remember, the gradient is the vector of all partial derivatives. Okay, the gradient of w then, since there are 3 variables here, we'll have 3 partial derivatives. So I want the partial derivative of w with respect to x, with respect to y, and with respect to z. If I put those in a vector, that will be the gradient function. Okay, so let's take the derivative of each of these separately, and then we could put them together in a vector for our final answer. Okay, so I need the partial derivative of w with respect to x. So here's our function w. I'm taking the derivative with respect to x, so x is my variable. The other 2 variables, the y and the z, I'm going to treat as a constant. Okay, which means z squared times y, that's all a constant, right? Constant squared times a constant is a constant. Sine of a constant is a constant. So this whole expression here, I can treat as a constant, which means since it's multiplying e to the negative 2x, I just have to take the derivative of this, and then this comes along for the ride. Okay, derivative of e to the negative 2x is e to the negative 2x, and then a little chain rule, I need to multiply by the derivative of the exponent, which is negative 2, and then the sine of z squared y comes along for the ride because it's a constant. We're treating it as a constant. Okay, partial derivative of w with respect to y. Now we're going to treat x and z as a constant and y as the variable, which means e to the negative 2x, that's just going to be a constant, right? E as a constant number to a power of some constant is still a constant, which means e to the negative 2x just comes along for the ride. And I just need to worry about the derivative of sine of z squared y with respect to variable y. Okay, a little bit of a chain rule here since it's not just a y inside the sine function. So the derivative of sine of something is cosine of that something times, according to the chain rule, times the derivative of the something. The derivative of z squared y with respect to variable y would be just z squared. Okay? And so if I were to tidy this up just for my final answer, I'd write it as z squared e to the negative 2x cosine of z squared y. All right, one more derivative to go. The partial derivative of w with respect to variable z. Again, e to the negative 2x, that's all going to be treated as a constant, so it comes along for the ride. Derivative of sine of z squared y, that does have a z in it, and we're treating z as a variable, so we do need to take the derivative of that, and we need a chain rule. Derivative of sine of something is cosine of the something, times, by the chain rule, we multiply by the derivative of something, derivative of z squared y with respect to variable z. I'm going to do a power rule on the z squared, I get 2z. And then the y I'm treating as a constant, so it just comes along for the ride. Tidy it up. I'll write that as 2yz. I'll change the order here just to put the y in front so we are in alphabetical order. E to the negative 2x cosine of z squared y. Okay, I've got my 3 partial derivatives. Now I just need to put them together in a vector to get my gradient function. So the gradient of w is going to be equal to, the first component is the partial derivative of w with respect to x. That's negative 2 e to the negative 2x sine of z squared y. The second component is the partial derivative of w with respect to y, which is z squared e to the negative 2x cosine of z squared y. And the final component of my gradient is the partial derivative of w with respect to z. That's 2yz e to the negative 2x cosine of z squared y. And that vector is my gradient. I want to finish this section taking a look at the same function we started with. And we looked at the first partial derivative, this partial derivative of f with respect to x, partial derivative of f with respect to y. Just like in single variable calculus, in multivariable calculus, it is often helpful to look at higher order derivatives, second order derivatives, for example. Okay, so let's take the second derivative with respect to x. Now, in order to take the second derivative with respect to x, I need to take the first derivative with respect to x, right? So I get 1/8. Let's see. Derivative with respect to y squared goes to 0 minus xy, so that'll be minus y minus 2x. Okay, one more derivative with respect to x. Notice our notation here. We are using double subscripts here. That means I have, the idea here is this, okay? I'm taking this function, which I already have the derivative of with respect to x, and I'm taking the derivative of that function with respect to x. Okay, that's what that double subscript means. We could also write this in the other notation we have. This would be double partial f, partial x squared. The idea here being that we're taking the partial derivative of x of partial f partial x. So I get two partials up top and two partial x's on bottom. Okay. So if I take the derivative of this, the 1/8 comes along for the ride. Derivative of negative y, that's just 0. Derivative of negative 2x with respect to x, that's negative 2. And so the second partial derivative is just a constant negative 1/4. Okay. What does that mean? Well, we're thinking about this as we are as the derivative of a trace where we are holding the y value constant, right? So let's take a look at this graph here. So this is the graph of our surface again. Let's hold the y value constant, say y equals 2. Okay. Now, what it means is it's the second derivative of this curve. Okay, actually, let me do it this way so that the x moves positive on the right. Okay, it's the second derivative of this curve. So it's the standard way we interpret the second derivative. It tells us about concavity, because if I look at the tangent lines, okay, you see this tangent line here starting off positive, but since the second derivative is negative, how are the slope of the tangent line changing? Well, if the second derivative is negative, that means, remember, the second derivative is the derivative of the derivative. So it tells us how the first derivative changes. And if this is negative, it's saying that the slopes of those tangent lines are decreasing. They're becoming less positive, they're becoming more negative. And we can see that happening. If we move this tangent line along the curve, we become less positive, we become more negative. Okay, just as in the single variable case, a negative second order partial derivative means that along that trace we're concave down. Okay, what about if we look at the second partial derivative with respect to y? So the first partial derivative, we get 2y minus x times the 1/8 in front. the second partial derivative, we still have that 1/8, and then the derivative of 2y minus x becomes just 2. And so we get positive 1/4. So that means that along any trace where we're holding x constant and we're looking at the change in y, that trace should have a positive second derivative. It should be concave up, right? Which means if we interpret this as how that first derivative changes, over time, that first derivative should be increasing, right? A positive second derivative means the first derivative is increasing. If the first derivative is increasing, that means the slope of the tangent line is increasing. An increasing slope means we're becoming less negative, more positive. Let's see what that looks like. Okay. So here's our surface. Let me go back to kind of our standard way to view it. This is an example of a trace where we're holding the x value constant. There's a tangent line. Let me pull that all the way back here. And let me hide the surface so this is a little bit easier to see. So again, just a single variable trace, right? Just the cross section gives us a single variable function. It's just embedded in 3 dimensions. And as we increase our k here, as we let the tangent line move across the curve, we can see we are indeed becoming less negative, more positive. And that tells us that the concavity of the curve is going to be positive. It's going to go up. Okay? So these second order partial derivatives just tell us concavity, just like first partial derivatives for the trace that they are describing. Okay? But because we have 2 derivatives, there are actually, or 2 variables rather, there are actually more derivatives that we could take. I've focused on only staying with the same variable, right? I took one variable with respect to x, then another variable with respect to x. I took one derivative with respect to y, then another derivative with respect to y. What if we mix them up a little bit? What if we mix the derivatives? What if I look at, take my partial derivative with respect to x and take another derivative of that with respect to y? In that case, I'm taking the derivative of this with respect to y. I have the 1/8 in front, and then the derivative with respect to y, I get -1. And then the derivative of -2x, I'm treating as a constant, just goes to 0. So I get -1/8. Okay? And I could do the same thing here. I could look at the second derivative, taking the second derivative of this with respect to x. So I take my first derivative with respect to y, and then I take the derivative of the result here with respect to x. So I have the 1/8 in front, and then the derivative of this with respect to x is just a -1. So it's also -1/8. What does that mean, though? How do we interpret this? So this is a little harder to interpret. Okay, so this means, let's focus on this one first. Okay, this means that I'm looking at my derivative with respect to x. Along those traces where I'm holding y fixed and I'm letting the x change, I'm looking at the derivative. But then as I move over, as I move the y, as I move, as I change the y, how does that change the slope of those tangent lines? Right? So let's get an example going here. And so let's see, change with respect to x first. So that would be y is held constant. Nope. Right here. Okay. So I want to start by looking at just one of these tangent lines. And actually, you know what? Let's go the other direction. It's going to be a little bit easier to see. Okay. So there's one tangent line in the direction of x. So I'm holding y constant. I'm letting x change. Okay. That's what this tells us. Slope of the tangent line where I hold y constant and let x change. But what happens when I look at those tangent lines and then I move in the y direction? So this is the tangent line where the y value is -5. What if I move the y value a little over? What happens to the tangent line? Okay. See that? Hide the surface for a moment. So our first tangent line there, notice it has a positive slope. Okay. But as I increase the value of y, what's happening to that slope? Now, if we look over, that slope, it's not quite as steep uphill, right? It's not quite as positive a slope. Let's add another one. Let's go a little further over. We're not quite as steep again, right? And as I keep on doing this, it starts to flatten out, then it becomes flat, and then it starts going negative. Okay? Starts going downhill. Right? So these are the slopes of the surface, the slope of the tangent line, but we're looking at them as we move across in the y direction. So the slopes are taken in the x direction, but we're seeing how those slopes change in the y direction. And in this case, we're seeing that the slopes are becoming less positive and more negative. And that's exactly what this is saying. As we move in the positive y direction, those slopes should decrease, become less positive and more negative. Okay? It's describing how the surface twists. We could look in the other direction too. Okay? Here, let me get the orientation right and hide the surface. Yes. Right? So here, slope of the line here, which is tangent to the surface, it's got a positive slope. As I move over, as I move this line from left to right, -5 to -4, notice the next line over isn't quite as steep, right? Not quite as strong a positive slope. And it gets less and less steep as we move along until it flattens out entirely and starts to decrease. Okay, the exact same behavior. It's the slope of the tangent line as we move from -x to positive x. The slope of the tangent line in the y direction becomes less positive and more negative. Again, it's describing how the surface twists. And if you look, there's actually the twists kind of match up, don't they? It kind of makes sense if you think about it for a little bit, that this and this have the same value. Because if we look at how the tangent line twists in one direction, it kind of is going to force how the tangent lines twist in another direction. Right? They kind of have to match. You can't twist just in the x direction and not twist in the y direction. Right? It turns out this is a rule. This isn't an accident. The mixed partial derivatives at a point will almost always be equal. There are exceptions, they're very rare. So let's state this as a theorem. Equality of mixed partial derivatives. Let z equal f of xy be continuous in some neighborhood of the point x naught, y naught. then, I'm sorry, it's not that the original function has to be continuous. Let me rephrase this. It's that the second partial derivatives have to be continuous. Let z equals f of x, y have continuous partial derivatives. Okay, wait, that's not quite right either. One more time. Okay, let z equal f of xy if the mixed partial derivatives f of xy and f sub yx of xy are both continuous. In some neighborhood of x naught y naught, then those second order mixed partial derivatives are going to be equal at that point. Okay, so it doesn't always happen that these mixed order partials are equal. For the purposes of this class, you can assume that it is always true. It is very rare where this doesn't happen, where the second derivatives are defined, but this does not happen. I can't even give you an example where it doesn't happen. If you want, you can Google it, but the example is too difficult. It is beyond the scope of this class. But if you want to find one of those rare situations where your mixed partial derivatives are not equal, you can Google it if you want. It is out there, but again, it's a little tricky. For the purposes of this class, you could assume that those mixed partial derivatives will always be equal.